Welcome to the Eviews tutorial for the 5th lecture, Research in Financial Markets. In this Eviews tutorial, I would like to go through how to run GARCH-in-mean models and how to test if a risk factor or if a zero-cost portfolio qualifies being a risk factor. So we remember from the lecture that the mean equation of the GARCH-in-mean model is given by equation 8, where we have on the left-hand side the zero-cost portfolio returns. Yeah, they are by default given in excess returns. And we have in the mean equation an intercept term alpha. Then we have the conditional volatility, here denoted as sigma, times the sensitivity, the loading against the volatility, denoted here as the gamma. Also, of course, because it's a model that has to be estimated, we have an estimation error, which is denoted here as the epsilon, yeah, the residual term epsilon. Then, of course, we have not only the mean equation in a GARCH-in-mean model, or any GARCH model has a separate equation for the volatility, which is the sigma squared at time t, conditional on time t, or t plus 1. And we have given this in equation, let me see, it's in equation 12. Okay, so that's the standard model for the variance, where we model the variance, the sigma square at time t, or here it's conditional on time t plus 1. We have the unconditional variance, which is denoted as delta 0, which is just an intercept term, which gives us the expected volatility if there's no innovation occurring and if the previous conditional volatility or variance is equal to 0. Yeah. So given that these guys, delta 1 and delta 3, are equal to 0, yeah, this delta null gives us basically the unconditional variance of that model. Again, we see this epsilon squared. It's the same like we have in the equation for the mean. Yeah, it's basically the squared residual of the mean equation that is also a part of the variance, yeah, which is the innovation part of the variance. Whereas this guy here, the last guy, is the variance conditional on time t plus 1 lagged, and then it becomes, of course, time t. In other GARCH methodologies, you might see that they have here a t instead of t plus 1. Yeah, if this is conditional time t, then we have, of course, we have to use the epsilon squared conditional on time t minus 1. And then this last term here becomes the variance, the sigma square, given time t minus 1. Yeah, so it depends a little bit on how you choose to write it down, on the notation, basically. Moreover, then I told you also during the lectures, the random part actually is the sigma, so the square root of this expression here, yeah, the square root of this expression times a normally distributed residual. In standard GARCH models, we assume that the innovation part is normally distributed. Yeah, we will see that in real life it's not, but we will come back to that soon. So now the question arises how to model this, the GARCH model, the GARCH-in-mean model in Eviews. So the variance equation here is the same like in any standard GARCH model. So the only thing that is different in the GARCH-in-mean model is obviously that we have also the variance here appearing in the mean equation. Yeah, and it can be either like here the volatility, or it can be the variance. Yeah, then it's sigma square, conditional on time t or t plus 1. So, and this is now what we will evaluate in Eviews. And I told you, so the condition is, first of all, that the sample average of what is here on the left-hand side, yeah, of the potential risk factor or the risk factor candidate should be positive, and in the GARCH-in-mean equation, the alpha, which is the intercept, should be 0, yeah, because if this is a risk factor, the returns, the return evolution should be fully explained by its loading against its conditional variance. Yeah, and this is derived in another paper of mine. Let me just check briefly where I can find this paper. It's in my folder, Klaus published papers, and it's a paper from 2016, which I co-authored with Jesper Hager from Hanken School of Economics. It's published in the journal Finance Research Letters. It's also an A journal. It's a good journal, actually. And you see the theoretical derivation here, yeah, in section 3. Yeah, that's the theoretical derivation, and of course the idea comes from the paper from Sharon-Rook and Conrad, the 2008 paper. Yeah, so now let's go back. So this is the data file. It's called data_garch_models. It's an Excel file that I will also provide you. You see here in the first column the market excess returns. Market minus risk-free rate is the market excess returns, and it's the CRISP index, of course, the US index. And we see we have 1091 minus 2. We have 1089 monthly observations. Yeah? Second column, we have the size factor. Third column, the value factor. What we have in column D, this is the risk managed short-term industry momentum factor. Yeah, so the 1 month spread using value-weighted industrial portfolios as input assets. Yeah? So this short-term momentum factor here is risk managed and based on value-weighted portfolios. In column E, what we see here is the unscaled counterpart. So this is the short-term industry momentum factor. Yeah, this 101 strategy you remember from the lectures, using value-weighted industrial portfolios as input assets. Yeah, so all of these factors here are related to the US stock market. Yeah, so let's use this Excel file and upload it in Eviews. Yeah, here we have opened Eviews. Go on File, New, Work File. So we know the data frequency. We choose again unstructured, undated. We have 1089 observations. Yeah, and we know already our observations start in 1927, and we have data until 2018 in our data set, right? We click the OK button. Then this wizard here pops up. We go on proc, import file, import from file, and then basically I have stored a copy of that file on the desktop. So I just go on the desktop and I double click data_garch_models. Then Eviews uploads this file, just push finish. Here we can push no. So now what we have here we have the HTML factor, double click, and it shows you the time series evolution of this vector. We have the market factor in excess form. We have the size factor. And resids, basically, if you double click, not available yet. So here, of course, Eviews stores, basically, if you run a regression, Eviews stores the residuals there. So you cannot, this is here always by default, this empty result vector, this empty resid vector. Then here, VW_1M_spread, this is our 010 strategy, our short-term industry momentum strategy using value-weighted US industrial portfolios as input assets. It's a zero-cost portfolio, obviously. And here we have the risk-managed counterpart. Okay, so now let's go on object, new object, equation, push the OK button. And what I told you already in the lecture, we have to estimate this model via maximum likelihood estimation. Yeah? So we go on Arch. Now that's the model class. Now we put in, let's first grab our unscaled risk factor. Yeah, if you just click VW, then this pops up here in Eviews. You can then just double click this. So now we have the unscaled short-term industrial momentum strategy. We include C, which is in Eviews denotes the intercept term. Okay, so that's our alpha of equation 8. Okay, you remember. So now arch parameters, here we have one arch. Arch parameter is the epsilon, the epsilon squared in the variance equation, and GARCH is the corresponding parameter related to the squared variance of the previous period, conditional on time t minus 1 or time t, depending on what is your notation. Yeah. So if we go back, let's just go here and open again the corresponding paper. So in Eviews notation, so our C in the mean equation measures our alpha, and in the variance equation, our GARCH term is this guy here. Yeah, and it gives us the point estimates then, of course, for this delta 3, and our arch term is the epsilon squared. Yeah, so the squared residual from the mean equation. Yeah, which is a measure for the innovation part of the variance equation. So this is then related to our delta 1. Yeah. Okay. So, and here arch M, this is here where we can choose our GARCH-in-mean model, because if we would run this model here, it would give us a plain arch 1 model, yeah, which having an intercept term in the mean equation. So let's use the standard deviation, yeah, which we have here also in equation 8. Yeah, so we have the standard deviation here. Yeah, it's the sigma. It's not sigma squared. It's the sigma, the standard deviation, the volatility. Let's use the volatility first. So then we get here for the mean equation 2 parameters. We get the alpha, and the gamma will be then the corresponding parameter estimate related to this arch in mean term. So error distribution, I told you already in the standard GARCH model framework, we usually have the normal distribution, the Gaussian normal distribution. Push the OK button, and what we will get is then these point estimates here. So this is our point estimates. The C is our alpha. Our alpha is estimated, point estimate alpha is 0.06, and the T statistic, or the Z statistic, is 0.24, rounded 0.24, with the p-value of 0.81, indicating that the alpha is statistically not different from 0. Yeah, so that's okay. But what about the gamma? Yeah, this is given here. Yeah, this is the corresponding parameter gamma. It's here in Eviews at squared GARCH, so it's the GARCH-in-mean parameter. It's a gamma, so it's 0.13 rounded, and the Z statistic is 1.58, or T statistic, and the probability is 0.11. So on the 5% critical, if we have the 5% significance level as a corresponding significance level for our testing procedure, p-value of 0.11 suggests that this point estimate is also statistically not different from 0. So neither the gamma nor the alpha are significant. So this means, obviously, the standard spread is obviously not, there's no, so the evolution, or the time series evolution of the premium or of the zero cost factor return is not related to its conditional variance. Hence, the standard unscaled short-term industry momentum strategy cannot be a risk factor. It's not qualified. It doesn't meet the necessary conditions to be a risk factor, because this gamma here should be significant. So the p-value should be below 0.05, right? So then, of course, we can play around a little bit with the model here. Yeah, we can use the variance instead. Yeah, now we would basically here in the mean equation, it's the same model, but now we have here instead of the volatility, the sigma squared conditional on time t, respectively t+1, depending on how we choose the notation. Okay, again, let's estimate the model and see what the corresponding parameter estimate, the gamma, would be. Push the OK button. Voila, same result. Okay, now it's even worse. We see that the intercept term, so in the mean equation, the alpha is statistically significant. Yeah, on a 5% level, we see the p-value is 0.02, and the GARCH term, so the gamma, our gamma, this is the point estimate for the gamma, because this is the parameter related to the GARCH term in the mean equation. Yeah, this models here the mean equation. These are the parameters for the mean equation. So the gamma is estimated at 0.01 rounded, and the p-value is 0.18. So on a 5% level, we would not reject the null hypothesis that this parameter is statistically not different from 0. So this parameter here is statistically not different from 0. But if it would be a candidate for risk factor, this guy here would be significant, and this guy here would be insignificant. So it would be exactly the other way around. Okay, so irrespective of the model specification here, yeah, so we have the same outcome. We can also use, again, we can even now include the Farmer and French 3 factors. We can include the market factor here in excess form, the SMB factor, and the HML factor in the mean equation. Everything else, we leave it as it is, push the OK button, and what we get is it's the same, qualitatively the same outcome. So the gamma is statistically not different from 0, but it should be significant. It should be significantly positive if this would be qualified as a risk factor. Okay. So let's check now our risk managed short industry momentum factor. Let's plug it in here as our dependent variable. This is now this guy here, VW underscore RM underscore 1M underscore spread. This is our risk managed or our volatility managed short-term industry momentum spread. Again, our C denotes the alpha in the equation. It's the intercept term. We start with the variance in the mean equation. With the standard deviation in the mean equation, which is here, the volatility. We leave everything else as it is, push the OK button, and what we get is this estimate. So we see the intercept term, the alpha, is estimated at minus 3.09 in rounded figures, but on the 5% significance level, this point estimate is statistically not different from 0 on a 5% level, because the p-value is larger than 0.05. So the t-statistic is above the critical value of minus 1.96, provided that the point estimator are normally distributed. On the other hand, we see that the gamma, the point estimator related to the standard deviation or respectively volatility in the mean equation, is estimated at 0.69 in rounded figures, and the Z statistic or the T statistic of 2.18 suggests that this point estimator is statistically significantly positive. The corresponding p-value for that test statistic is 0.03 in rounded figures. So on the 5% level, we reject the null hypothesis that this guy is 0, hence it is significant, and it implies that this risk managed short-term industry momentum is qualified as a risk factor given this model framework. Again, we can now put the variance here in the mean equation, so the sigma squared conditional on time t respectively t+1. What we have to do is here then we plug in here as GARCH-in-mean variable, we put in the variance instead. We leave everything else as it is. Again, we assume normally distributed innovation process. Yeah, you remember on the whiteboard it was the U, right, in the third equation. So we push the OK button, and what we see, the same thing. Okay, it's qualitatively the same thing. So the alpha, which you see denoted as C in our Eviews output, it's minus 0.90 in rounded figures, and the p-value is larger than 0.05, which means that we cannot reject the null hypothesis that this point estimator is statistically not different from 0. Okay, this guy is insignificant, but our gamma, so the loading against the variance in the mean equation, yeah, this guy, is 0.05. It's positive. Yeah, it's in line with the sample average of the spread, which is also positive. And the Z statistic is 2.22, and the p-value of 0.0267 suggests on the 5% level, we have to reject the null hypothesis that this guy here is 0. Hence, we accept the alternative hypothesis suggesting that this point estimator is statistically significantly positive. Hence, this guy here, hence we can conclude that this risk-managed short-term industry momentum factor qualifies as risk factor, irrespective of this, if we which model specification we choose. Now what we can also do is, again, we can here control for the pharma and French risk factors, the market factor in excess form, size factor and value factor here in the mean equation. We leave here the variance as a regressor in the mean equation, push the OK button. It's the same outcome here, okay? It's qualitatively the same outcome. So we see that our alpha is statistically not different from 0. Now the p-value even increases, which is even better. And here we see the gamma, the point estimator corresponding to our GARCH-in-mean model here, is positive and on a 5% level significant. So the problem is, okay, let's push the OK button here. Let's go on prox, make standardized. We want to make the standardized residual series. Where can we find it? Resids, objects. Make residual series standardized. Yeah. Okay. So these are our standardized residuals. This is our estimated innovation process. Okay. On the whiteboard, you remember it was in the third equation. Yeah, it was where we modeled the square root of sigma t is or no, wait, it's where we modeled the epsilon t is equal with the square root of the variance squared at time t times the innovation times the ut. This ut is normally distributed with mean of 0 and standard deviation of 1, right? So this is what we should get here. This is our estimated residual term of that equation. And let's go on descriptive statistics, histogram, and stats. And we see here the mean is basically 0. Yeah, it's 0. And the standard deviation, which we see here, is 1. It's exactly how it should be, but that's by construction. So this is what the GARCH model will always spit us out. So we have always an innovation process that has sort of 0 mean and a standard deviation or a volatility that is equal to 1. But what about the kurtosis? Yeah, we know from a normal distribution, the skewness is 0 and the kurtosis must be 3. There's no other distribution, at least not as far as I know. If you know, let me know. But if the skewness is 0 and the kurtosis is 3, we would have a thin-tailed or a standard normal distribution, given mean is 0 and volatility is 1. So the Jacques-Barra tests basically the skewness and the kurtosis together. Yeah. So under the null hypothesis, skewness is 0, kurtosis is 3. Yeah. Whenever this the test statistic is large, or we can also read it here from the p-value. When the p-value is below 0.05, it would tell us that the distribution is not normal. So because under the normal distribution, again, under the null hypothesis, again, we assume that it's normally distributed, and the normal distribution has skewness of 0, totals of 3, and whenever this is violated, significantly violated, then the probability of the JB statistic would be or the p-value would be below 0.05, given that we have a significance level of 5%. Yeah? And here, obviously, we see that our innovations are not normally distributed. They have fat tails, so-called fat tails. They are almost not skewed. Yeah, the skewness is close to 0, but they are fat-tailed. Yeah, so the normal distribution is the wrong distribution. Yeah, so we make wrong inference if we use the wrong underlying distribution. Okay, so the values for the for two standard deviations from the mean are different for a fat-tailed distribution. Okay, so actually what we have to do is let's go back to our stats here. Go to proc estimate. So let's take the standard model in the mean equation. Let's take away the value factor, size factor, and market factor. So let's just have the standard GARCH-in-mean model, yeah, where we have the variance in the mean equation. Or we can also just take the standard deviation, doesn't matter. What we would be supposed to do is, in order to make it correctly, we have to change the error distribution, which models this innovation process, yeah, that makes the whole GARCH model actually a random model. So we have to plug in basically students T, and let Eviews choose the optimal degrees of freedom. We know that the students T distribution is dependent on the degrees of freedom, and if we choose this option here in Eviews, students T, then Eviews gives us the optimal degrees of freedom. Yeah, so it basically searches for the number of degrees of freedom that basically fits this residual process the best. And we know a T distribution has fat tails. Yeah, it can be modeled as fat tails. And if we use this distribution here and push the OK button, we get the corresponding estimate using the T distribution. And we see here, yeah, based upon this estimation procedure, maximum likelihood, and having optimal degrees of freedom, a T distribution with 5.2 degrees of freedom. Yeah, and we see here the degrees of freedom are significant. Yeah, so this is the correct, or at least more correct distribution. Yeah, we see that in our mean equation, the alpha is still statistically not different from 0. Yeah, so which is good news, but the gamma, yeah, which is this guy here, which should be positive, it is still positive. Yeah, it doesn't change the sign of the point estimator, but we see that on a 5% level, it's not any longer significant. Yeah, so having a 5% significance level, we cannot reject the null hypothesis that this that the gamma is also not different from 0. Okay, which is bad news. We can also choose the degrees of freedom. Yeah, if we say, okay, let's take let's take a T distribution which has also fat tails, but which has a little bit less fat tails than the T distribution with 5 degrees of freedom. So let's choose a T distribution with 10 degrees of freedom. So, and if we choose a T distribution with 10 degrees of freedom, okay, then so we impose 10 degrees of freedom for the in order to model the fat tailness of the innovation process. What we get then is again, the alpha is now statistically not different from 0. P-value is 0.13, which is larger than 0.05. So this is what we would expect. And also here the gamma is positive, and it's significantly positive. Yeah, exactly as we had with the normal distribution. Yeah, so the p-value is below 0.05, and we would say, okay, evolution of this risk managed short-term industry momentum is fully explained by its conditional variance. Yeah, even if we choose a t-distribution with 10 degrees of freedom. Also, what we can do is we can choose now we choose the variance, and again we let take care of we let Eviews determine the optimal degrees of freedom. Everything else remains the same. We just choose now here in the mean equation the sigma square instead of the volatility. Everything else remains the same. Push the OK button, and what we get the same, a very similar picture. Yeah. So the alpha is statistically 0 on a 5% level, and the gamma is also, it becomes slightly insignificant. Yeah, we see here the loading is positive, as it should be if this is a risk factor, but the p-value suggests 0.058 is slightly larger than 0.05, implying that on a 5% level, we would not reject the null hypothesis that this gamma is also 0. Yeah, so depending on how we model the error distribution, yeah, we would come obviously to different conclusions. Yeah, we can also choose again here in the mean equation. We can choose to control for the Raman French risk factors. Remain everything else should be the same. Again, push the OK button. OK, and now it becomes again an outcome that we enjoy to see. Okay, after controlling for the Raman French risk factors, where we see that the size factor has a significant exposure, obviously, which implies that since the point estimate is negative, it implies that our strategy is obviously exposed to the short side of that factor. So it is invested in big stocks, or in industries that have big stocks, more precisely. But what we see here, the interesting point is again the alpha, which is here given by C in our Eviews output. It's negative, but the point estimate is statistically not different from 0. So it's statistically 0 implied by the p-value of 0.47 in rounded figures, and we see that the gamma, which is the corresponding estimate here, that we are interested in, this should be positive when this is a risk factor, and we see it's positive, and the Z statistic, respectively the p-value, suggests that this point estimate is statistically significantly positive, implying again our original conclusion that this strategy qualifies as a risk factor. Yeah, after we control for the Farmer and French risk factors, and provided that we have the correct distribution for our innovation process, which is a t-distribution with 5.3 degrees of freedom. Yeah, having heavy fat tails. Okay, that's basically what I would like to talk with you in this short Eviews tutorial. So you see, you have to be careful how you model your GARCH model, and depending on how you choose the model setup, you get obviously different significances in your parameters. Yeah, it's important to note. I mean, GARCH model can model any time series. Yeah, a very good in sample. Yeah, but it doesn't mean that it works out of sample. Yeah, this is more a tool for in sample analysis. And if I have just recently understood the importance of the error distribution of the innovation process. So if you want to really to satisfy, or if you want to show that your results are robust, the thing is, in financial markets, there's hardly anything that is normally distributed. Time series or financial time series are heavily fat-tailed distributed. So daily returns, for instance, there are papers who are stating that daily returns are approximately distributed as T distribution with 3 degrees of freedom, which is even more fat-tailed. But here we have monthly returns, obviously, and our optimization procedure tells us, our maximum likelihood procedure tells us, okay, these monthly returns are modeled, or can be modeled, by a t distribution with 5.3 degrees of freedom, which is slightly less fat-tailed than daily returns. But anyways, we have fat-tailed distributions, and if we would choose here a normal distribution, we would end up with wrong inference for our point estimators here. So we are always on the safe side if you choose here a student t distribution. Yeah, and if you have very good reasons for choosing a degree, the degrees of freedom by yourself, you can choose here the use students with fixed degrees of freedom, then you plug in how many degrees of freedom you want to have in your estimation procedure. Okay, so that's what I would like to talk with you today. Yeah, thank you for your attention.